Lieber Uli, vielen Dank. Es macht mir eine besondere Ehre und große Freude, in Berlin zu sein und um die Metric B zu bauen. You will see that I plan to improve my German in the next 3 years, but also try to learn from lots of brilliant people who work in the space of trying to improve research practices. So the talk is going to be in English. Science is clearly the best thing that can happen to Homo sapiens, but doing research is quite a demanding process. Research may not be reproducible and may not be useful. It may be reproducible but still not useful. Ideally, it should be both reproducible and useful, and an open question is whether it can ever be non-reproducible but still be useful. And I'll try to go through these possibilities. A simplistic narrative is that science is completely powerful, omnipotent. Scientific discovery is easy, and everybody's waiting new discoveries on a daily, if not hourly basis. This narrative often coexists with some urges. One is the urge to rush. Patients are dying. Let's please license new drugs immediately. To be methodologically sloppy, for example, use routinely collected data instead of randomized trials. To make a god of data, just data for the sake of data, and also give financial value to data. I mean, currently the most expensive thing on earth probably is considered to be data, instead of scrutinizing that deity and that expensive construct. And importantly, to avoid replication as me too unimportant effort. So, you know, that perspective is equivalent to what you would see in artistic cycles, in aesthetics, in art, where if you have two paintings that look like one is a copy of the other, one is the original, and it is worth several millions of dollars if it's by a great master. And if the other one is a copy, you know, you can buy it for €2 and just hang it in your bedroom or toilet or wherever you want. It has no value at all. It's just a replica. It's just a replication. Now, is that true? Well, we can do a little bit of modeling. We can try to model the value of discovery and the value of replication. And this is an equation for the value of discovery. It's proportional to true positive minus h times false positive, or equivalently r times base factor minus h, where r is the pre-study odds of a research finding when we're searching and running lots of analysis. Base factor is the base factor that is conferred by the discovery data. And h is the ratio of the weight of negative consequences from false positive discovery claims versus the positive consequences from true positive discovery. R and H are pretty field specific. If I'm working in a field that has very few things to discover, I'm stuck. You know, I chose the wrong career, but that's it. You know, that's nature. If I was lucky to pick a field where there's a lot of things to be discovered, again, I was lucky, but you know, again, that's nature that I'm facing. Also, the ratio of consequences is pretty specific to the field, and obviously can be different across fields. The one thing that we can change is really the base factor, is really the information content of our data, of our studies, what we try to get out of the research investigation pipeline. In that framework, many discoveries may have negative scientific value unless they're replicated. We may increase the base factor by running larger studies, by ensuring greater protection from biases that would erode the credibility of the results. But to avoid negative values for the overall value of discovery, one needs a base factor to be more than h over r. And if you think through different scientific fields, you will quickly realize that this is difficult, if not impossible, in the absence of replication. Most original discoveries come from small studies where biases are very common, base factors are unavoidably pretty small, and more often we're dealing with situations where the R values, the pre-study odds, are not really very high. And the more exciting fields actually may have very low R values, which means that success is difficult but very interesting to arrive to. So we need replication to increase and even to set a minimum standard of scientific validity. We need research that is reproducible across multiple studies, across multiple approaches, or both. And here comes reproducibility with a set of confusing terminology that people may use in very different ways. So there's reproducibility per se, there's replication, but there's different types of replication, including exact replication or conceptual replication. There's reanalysis, there's repeatability, there's corroboration, there's triangulation, and there's also other terms that are circulating in the literature. Most of these terms have acquired a lot of popularity. People use them in different connotations. This is some empirical data looking at reproducibility of results as a phrase, or similar phrases, or research reproducibility. Across all 22 major fields of science, there is an increase over time in the utilization of this terminology. However, reproducibility could mean very different things. The three main bins are reproducibility of methods, of results, and of inferences. So reproducibility of methods is about the data plus software plus script plus methodological tools that if you put them together for the very same study, you should be able to recreate the same result out of that single experiment or single study. It's largely a computational phenomenon that we're trying to validate. And this means that you need to have the ingredients in place. You need to have the data, you need to have the software, you need to have the script, you need to have the methods. Be able to understand the methods through the fine print of the method section and be able to implement them. Reproducibility of results is probably closer to what many people are using the term replication in another study to describe, which means that we try to do another study and see whether we get similar results. And then the question arises, well, will you do exactly the same study? Can you even do exactly the same study? Do you want to deviate a little bit? And what is a little bit? Do you want to deviate a lot? And if you deviate a lot, then how do you know if you get or do not get the same result, whether it's the deviation that caused that diversity? And finally, reproducibility of inferences is the making of knowledge claims of similar strength, or conversely, very often of very dissimilar strength or very dissimilar connotations. When you have a body of evidence, a body of study results, you ask 100 people, what do you make out of that? And some people are very enthusiastic, others are more skeptical, and others are extremely skeptical sometimes. One size does not fit all across all science. There's differences across fields that affect further what reproducible research might mean. We may have different goals in different fields in terms of what is the degree of determinism that we would be seeking, the signal to measurement error ratio that is inherent in the type of data that we are collecting, the complexity of the designs and the measurement tools, the closeness of fit between hypothesis and experimental design and data, the statistical and analytical methods to test hypotheses, the typical heterogeneity of experimental results, whether there is a culture of replication, transparency, and accumulating knowledge, what statistical criteria we use to make claims or to interpret the data, and finally, is that just a curiosity or is it something that has application? Is it affecting human lives? Is it affecting communities, society? What are the consequences of false conclusions if we don't get it right? Science is a vast universe of multiple galaxies. Some of these galaxies communicate more with each other, others are very remote and maybe have never joined forces. Does this mean that they use different methods? We all use the scientific method, but each galaxy in that universe is interested in different aspects of the scientific method and may be more fierce in defending some aspects of the scientific method compared to some others. Even for galaxies of disciplines that are pretty far apart and possibly never communicate in joint projects, they never have joint conferences or joint professional societies, some of the problems that they're facing may be very similar. And if they're similar, one might argue that maybe the solutions to these problems may be the same, or again, very similar. For example, many fields in neuroscience, psychology, cognitive psychology, or related medical fields suffer from running mostly hugely underpowered small studies that may lead to very questionable inferences, both for false negatives and for false positives and false negatives. Economics, which is so far apart, so many light years within that universe of science, when it comes to observational economics, seems to have a very similar problem much of the time. Very small studies with very complex questions that are unlikely to have even minimal power much of the time to have decent ability to arrive at reliable results. Replication has started becoming more popular in some fields, but not others. When we have fields that have adopted replication in large scale, we can go back and ask what has happened to the research findings that had been claimed before the adoption of a replication culture. Whenever this has happened, in my experience, whenever fields have adopted replication practices, they find that most of the initially claimed statistically significant effects that they had encountered in the pre-replication culture adoption era were either false positives or substantially exaggerated. Genetics is one such field where replication became a sine qua non. It was very easy, it was very cheap when the genotyping costs went down more than 1 millionfold. And when we decided to join forces and create very large genome-wide association studies in large consortia, going back and trying to see what was the replication rate for the original publications of the Candida gene era that had several tens of thousands of papers published in top journals like Nature, Science, and all the leading specialty journals, the replication rate was 1.2%. Many other fields have not seen that shift to a culture of replication, so one wonders whether their performance would be better than that. I mean, was it that geneticists were just so awful and had no clue about what hypotheses and what research targets they were choosing, and conversely, nutritional epidemiologists are so smart, 100 times smarter than geneticists in picking their targets, or some other field is outperforming everyone else. Preclinical research has also been going through a replication revolution. This time it has started mostly from the industry because lots of efforts from academic medical centers published in top journals seem to be very difficult to reproduce in the hands of the industry, and they were investing large amounts of money trying to take these leads to develop new interventions that they would market, and just couldn't get that done. So the reproducibility checks on preclinical research have shown success rates from 0 to 25% in most of the series, leading to claims like this one when only 6 of 53 landmark studies of Amgen oncology drug target projects could be replicated. The conclusion was that the failure to win the war on cancer has been blamed on many factors, but recently a new culprit has emerged. Too many basic scientific discoveries are wrong. Psychology has been going through a lot of soul searching and a replication, reproducibility transformation over the last 5 years. You're all familiar with the work of the Open Science Collaboration, trying to reproduce 100 creme de la creme papers from top journals in the field. You can read these results in very different ways, but roughly 2/3 of the time, 60%, or a bit more, the original claim didn't seem to be squaring with the subsequent reproducibility check, and the effect sizes on average were a bit less than half of what had been observed in the original study. Here's another series of reproducibility efforts in social sciences at large for papers published in Science and Nature. One might wonder whether these are the top, highest impact journals. Maybe they do a better job in filtering the research that they publish and they're more reliable. Not really. The average effect size is about half of what was seen in the original paper that was published in Science or Nature, and it seems that there's two groups. One is a group that the subsequent reproducibility effort shows nothing, an effect that's very close to the null and with pretty tight confidence intervals. And then there's another group where, on average, about 75% of the original effect is seen in the reproducibility effort. So something seems to be there, but on average smaller compared to the original. How much of that is an issue of genuine diversity, even though we do try to reproduce experiments in the series that I showed you very carefully and doing as exact a replication as possible? Obviously, a new experiment is a new experiment, so it's not going to be the same. So how much of the diversity is genuine and how much of that is bias, how much of that reflects error or a false signal in the original study, or could it be the reproducibility check that is wrong? I think that we're still scratching the surface, but here's some valuable data from the Many Labs 2 experiment, where instead of just having one effort to reproduce some creme de la creme results, multiple teams, multiple labs tried to reproduce results. And you see a pretty similar picture of about half and half, half empty, half full reproducibility, and pretty consistent results across labs. So it's not that most of the variability is explained by different labs getting different results in the reproducibility attempts. They may vary a little bit, but the main driver is that once you don't agree with the original, most of the time all the labs do not agree with the original. If they agree with the original, most of the time most of the labs do agree with the original claim. So coming back to the art example, here's the original. This is Andrea Mantegna, one of the greatest Renaissance painters, and his work on the visitation of Christ to the temple is in the Gemäldegalerie, walking distance. I visited again yesterday. I love that museum. So the original is really wonderful, but if you visit the Gemäldegalerie, there's a very nice exhibition of Mantegna and Bellini, and this is Giovanni Bellini, who's also really an amazing Renaissance painter, and that is also an original in Venice that was brought to Berlin for the comparison, so you can see them side by side. They are very, very similar, and they're both very, very important and very influential in the history of art. What actually happened is that Bellini did try to replicate exactly what Mantegna had done, and if you superimpose the two paintings, the drawing of the 6 central figures is exactly the same. Now, why was that? Well, maybe there were some family reasons. Maybe the prototype for the Virgin was Nicolosia, who was the wife of Mantegna and the sister of Bellini. And you may also see that Bellini has added a bit more. It's not just an exact replication, but has added a couple more figures, maybe some more family members in there. So both of these efforts have tremendous value. Both of them are original, and both of them should be seen at an equal setting, even though one was done first and the other one was done subsequently. And I think that if that can happen in art that is supposedly so individualistic, and you really strive for the most original and unusual and uncommon type of creativity, why not in science, where we seek even more objectivity? Different fields are working with different types of bias. And bias is very difficult to unearth. One way to address bias is to look at multiple studies that have looked at the same question and compare their results and see whether differences in their results are compatible with patterns that are suggestive of particular ways that bias might operate. So this is what we did in that exercise. We took all the situations we could identify across all scientific fields where meta-analysis had been performed, and this means that people had thought that some studies were similar enough to address the same question so that they would put them together in the same pile of analysis. And we said, well, if bias is operating in any of these 17 different ways, what kind of differences do we anticipate to see on average when we compare results of one study versus another? It's a soft signal. It's an averaging signal. It doesn't mean that if you pick a signal, there's bias specifically in that topic of that sort. But if you look across hundreds and thousands of topics and you see some persistent pattern, then that suggests that maybe this type of bias is operating in that particular field. Fields have different preferences for biases. So small study effects, which means that small studies tend to give stronger effect sizes compared to larger studies, is a phenomenon that is very common in the social sciences. It's pretty common in the biological sciences. It's uncommon in the physical sciences that are used to running experiments that are collaborative with extremely large sample sizes of observations and just sharing data from these huge telescope data sets or particle physics on collisions on zillions of particles that have been observed. Some biases are more consistent across all fields of science, others are more idiosyncratic. So the question is, can we map the potential biases and then tailor our response to try to optimize the performance of each scientific field and then multiple fields at the same time? Why do we need that? It's not just curiosity. In many scientific fields, we really expect to gain utility from science. Science has transformed our lives. In medicine, this has been a major success. Over time, lifespan has expanded rapidly over the last couple of centuries in particular, and some of that success probably has to be attributed to successful science. However, translation proceeds at almost a glacial pace. If you take the creme de la creme of clinical research, the most highly cited papers across the entire biomedical literature, over 1,000, sometimes over several thousand of citations each, and you try to map how long it took from the first basic science discovery to reach that point, which is shown here with the red vertical lines, on average it took 25 years. And in some cases like nitric oxide, it took about 200 years. There are exceptions. There's things like triple therapy in HIV infection, where it took only 4 years from the time that a protease inhibitor was developed with rational drug design until we had results from randomized experimentation, randomized clinical trials showing major benefits in survival. I was involved in ACTG 320. I was at NIH at that time, and I still keep that exciting experience of seeing a major clinical trial showing a fantastic reduction in mortality for what is an previously unavoidably lethal disease, completely transforming the landscape of a disease to become something that you can live a normal life with. How can we get more such successes? How can we move to getting these positive stories like HIV treatment being effective, as opposed to many other situations where it takes many, many years, and even when we get a very nice looking result in a seemingly very good study that gets heavily cited, it may still be refuted by even bigger, larger studies that are done subsequently. As shown here, in about 40% of the cases, you have these black points that show situations where the claim found in the highly cited clinical study was not really supported by even better and larger studies that were done. So we need useful research, but utility is not easy to get, and it goes beyond reproducibility. I may have reproducible research that I can see a phenomenon again and again, but maybe I cannot make any use of that. How can I determine if I have useful research? These are 8 rules to consider. First of all, is there a problem to fix? In medicine, in health, is there a health problem that is big and important enough to deal with versus are we just creating a new problem that doesn't exist and we shouldn't be caring about? I very often see that we produce a lot of information that is creating new conditions that people should worry about, but maybe they shouldn't worry about. We're just trying to make everybody sick in a way. But I'm not sure that this is a good strategy. Context placement. How much evidence do we already have based on previous studies, and do we really need a new study? I mentioned that replication in many cases has started being adopted. Sometimes we see just too much replication. We start seeing like an epidemic of the same study happening again and again without really moving any step further. And in that case, I would argue that maybe we don't yet need one of the same. Sometimes you even see meta-analysis being produced massively. There are some topics that there's over 100 meta-analysis done on the very same data. Information gain. Is the proposed study large and long enough to be sufficiently informative? Pragmatism. Are we reflecting real life? And if our research really deviates from real life, does it matter? Can we still make conclusions that would be applicable to real life? Patient-centeredness. Are we reflecting? Are we interested in patient priorities? Have we asked our patients what they want to see done? What is that matters to them? Or is it that we have decided kind of arbitrarily about priorities that they don't care? Is the research worth the money? Very rarely assessed. There's a lot of fields that spend tremendous amount of money and others that are probably heavily underfunded, and their potential probably would be inverse compared to what is happening for their funding. Feasibility. Can we do it? Clinical trials are often abandoned because of futility. About a third of randomized trials in surgery don't get anywhere because they fail to anticipate what they can do in terms of recruiting patients and participants. And finally, transparency. We're back to that issue of trust. Can we trust the methods? Can we trust the data? Can we trust the analysis? Are these verifiable? Are these unbiased? Or we're doing that in a vacuum? Empirical studies suggest that most of the clinical evidence is not of very good quality, and most of the clinical evidence is probably also not useful. If you look across systematic reviews, for example, covering the entire medicine in the Cochrane database, we did an exercise where we looked at close to 1,400 systematic reviews published over a year and a half. Only 43% of them had grade assessments, which is grades of recommendation, assessment, development, and evaluation. The others, most of the time, they just had no evidence to start with. So if you have no evidence, what are you going to assess and grade? The quality of the evidence for the first listed primary outcome was high only 13.5% of the time. And even when there was high quality of evidence, and even when we asked for significant results and a favorable interpretation of the intervention, like this intervention that is good enough to use it, we found only 25 such cases, which is less than 2%. High quality, significant results, and actionable results, at least based on the conclusion of the review. How do we improve the situation? There's lots of ideas, there's lots of research practices that have been tried out. Many of them are already very successful, and the question is, how can we take success stories and get them transplanted also in other fields that have not tried them yet and may have similar patterns of operation so that they might benefit? And how do we scale successful research practices that have been tried in a given field but are still limited to a minority of the research that is being done? So this is a dozen families of research practices that may help increase the proportion of getting true research findings. These include large-scale collaboration, adoption of replication culture, registration at different levels for studies, protocols, analysis codes, data sets, raw data, and results, sharing of data, protocols, materials, software, and other tools, reproducibility practices and reproducibility checks, containment of conflicted sponsors and authors, more appropriate statistical analysis, standardizing the definitions and the analysis across a given field, more stringent thresholds for claiming discoveries or successes, improving of study design standards, improvements in peer review, reporting and dissemination of research, and better training of the scientific workforce in methods and literacy of design and statistics. Large-scale collaboration has been very helpful and has worked in many fields ranging from particle physics to astrophysics to genomics. When there's a transition from small teams joining forces to create larger teams and collaborative structure, sometimes there is a shock, because I've seen very often that some of the glorified results of the past very quickly get overturned. In my experience, when I try to launch such collaborations, the first questions that you ask very often is, can I replicate the classics in the field? So I recall when I started doing research with collaborative consortia in genetics several decades ago, we started from the classics, and usually the classics could not be reproduced. And it really took extra effort to convince the community that, well, indeed, the classics are not reproducible, but if we continue down that path, we will find something that is more reliable and more consistent, and that we can put more trust on. But that transition phase, where the field goes through a shock, is something that one needs to endure and survive, in a sense. And hopefully, if the new methods find some more consistent signals, then that really helps. Levels of registration can vary. I'm not arguing that all research should be pre-registered. There's a lot of research that is exploratory, and we just need to acknowledge that this is what it is, that was exploration. It was done with no preconceived plan. We just iteratively went through a number of forking paths, and this is what we have arrived at. We kept some notes. Here they are. Someone may want to test that in a reproducibility attempt. There's other levels that include registering some of the pieces of the research. One level is to register a data set. I have described that as describing your nuclear arsenal, saying that I have 1 million observations with 1 million variables in each, so that makes for 1 trillion data points, and I can launch all these zillions of p-values against you if I push a button tonight. It's like describing the amount of dangerous content within a data set. Level 2 is registering a protocol. Level 3 would be registering an analysis plan, which I see as separate from a protocol, because a protocol very often has no analysis plan. So this leaves tremendous degrees of freedom for the analysis and on how exactly it's going to be conducted. Level 4 would be a registration of both the analysis plan and raw data. And level 5 is open live streaming, where one is sharing with the rest of the scientific community everything that is going to be done next day for feedback. It is revised based on that feedback, and then experiments happen and get fed back to the scientific community for further feedback for the next steps. In the absence of some planning, I have become increasingly worried that many types of research designs, even when they're used by the best scientists in the world, they can get almost any result. It is becoming very dangerous, almost ridiculously dangerous. I have seen that in my own work, in data sets that I have access to, and I can't believe that other data sets would be that different. The term that I use to describe this is vibration of effects, because instead of having one effect, you see the effects vibrating and becoming larger or smaller, or getting completely opposite results compared to one original result. And if you get opposite results from the very same data set on the very same question, I have turned the name Janus phenomenon from the Greek-Roman god who could see in two opposite directions. Here's one example from the National Household Survey in the US. If you look at the far right plots there about the association between alpha-tocopherol, vitamin E levels, and the risk of death. You have the hazard ratio on the horizontal axis and the minus log 10 p-value on the vertical axis. And there's 1 million data points shown in that plot. The way that we get 1 million data points is that there's at least 19 other things that could affect potentially mortality. So if you include or not include each one of them, you have two choices. So 2 to the 19th is about 1 million different models. 70% of these models will conclude that vitamin E decreases the risk of death. 30% of these models will conclude that vitamin E increases the risk of death. So unless there's some pre-specification, unless there's some rule, some guidance, some consensus in the field that has been agreed before really looking at the data, before inspecting and playing with the data, you can get almost any result you want almost any time. And I think that this is probably what we see in many fields that have these continuously contradictory pieces of information floating around both in scientific journals and in the news. This is one paper that had one of the 20 highest altmetric scores across all the scientific literature last year. Basically, it concluded that with 3 cups of coffee per day, your risk of death decreases by 17%. And I have an open pledge to the investigators to give me the data, and I will show you that with 3 cups of coffee per day, your risk of death increases by 17%. Sometimes the analytical model could be so influential that even with seemingly more rigorous study designs like randomized trials where supposedly you don't need to worry about adjusting for potential confounders, you may still get different results depending on who is analyzing the data and how the data are being analyzed. A famous study is 329, a study of paroxetine and imipramine for treating major depression in adolescents. It was a study that was published initially in 2001 by Smith, Klein, Beecham. It concluded that both of these antidepressants are very effective and very safe. And 15 years later, independent investigators looked at the very same data set. They asked the same question, and they concluded that both of these antidepressants are not effective and they have serious harms in that very same population that was originally studied. Not different patients, exactly the same patients, exactly the same data set, just analyzed by a team that had no reason to want to show that these antidepressants are really such great interventions for adolescent patients. How often do we have the ability to get hold of the original data to do reanalysis? I think the landscape is changing. If I were to answer that question even 3 years ago when I gave a talk in that very same hall, I would say we're struggling. We don't have almost any raw data from clinical trials, with very few exceptions. However, in these 3 years, there's been a lot of change. Some journals like PLOS ONE and BMJ, for example, have adopted policies where in order to publish a clinical trial, a default that is required is to make the raw data available to anyone who has access to them. And we did that. We asked all the investigators who had published in BMJ and PLOS Medicine under that new policy to share the data with us, and we reanalyzed their data for the very same conclusions and the same PICO, the same clinical question that they had addressed in the original publication. So we repeated the experience of study 329, but multiple times. About 50% of the investigators share their data, to be exact 46%. You can see that as half full or half empty, but compared to my experience even 5 years ago, it's clearly much better. And we did identify some errors in some of the analysis, but none of them were as starking as study 329, that they would invalidate entirely the conclusions of the whole investigation. This is a select sample. It comes from journals that have this policy. It comes from investigators who are willing to share. It is the data that they have shared. And I bet that, probably they took a last-minute look to make sure that they're not sending us something that would lead to a completely different conclusion to what they had published, hopefully. But it shows that there is a paradigm, there is a way to do that. It can be done efficiently. And some of these reanalyses can be done in very little time and with very little effort. I've heard the complaint that who's going to do that? It will take forever. If you have a plan in place, it can be done in no time. For example, the reproducibility effort for papers published in Nature and Science, everything could be reproduced for the whole paper within 30 minutes, practically, because there was a specific plan, a specific code that had to be run to just rerun everything by an independent investigator. What are the obstacles? There are still obstacles to sharing. Along with Tom Hardwick, who will be in Berlin full-time for Metric B, and Tom is here today, we did that analysis where we tried to find the raw data from the most influential, the highest impact, the most cited papers in psychology and psychiatry. So we aim to create what we call the data arc for these very influential papers. We had a little bit of success, but not as much as I would hope. Some of these data were already available, and a few more data sets were contributed to the data arc. Most of the time when they were contributed, they would be open to anyone to use. A few times it was just allowed for us to be able to use them, but at least they could be salvaged somehow in a repository that is made to remain functional even if humankind were to disappear, in a sense. If an alien civilization were to visit the planet, they would come across that system, that the databases will be still there. Well, maybe that's a bit excessive, but that's the rationale behind it. So what were the reasons for the rest of the studies that were not possible to retrieve? Very often, the decision to share was outside of the researcher's control, which I find very worrisome, and I've seen that in multiple fields. Very often, the principal investigators, especially in research that is done in collaboration with industry, they have no control of their data. Very often, they have never seen their data. Someone has analyzed them, but they have never really seen the data. There's a trust agreement, but as I showed you for 329, that trust agreement may not be so safely placed. Sometimes there's legal or ethical concerns, and I can take that argument, but this means that as we design new studies, we need to take that into account and try to make sure that the utilization of data would be maximized and that people will be informed, especially when it is patient-related research, that there is some very careful thinking about the ability to use the data. In some cases, the investigators were preparing their own sharing system. A few times the data no longer existed, a bit like the old paradigm in the Lancet about 25 years ago, where the data had been eaten by termites. That was the justification of the investigator. Insufficient resources, and finally, researchers using the data, even though these were studies that were done many, many years ago, but researchers were still using them, they would not share until they were really done with them. There's many data sets that are very influential that researchers have published over 1,000 papers, and they're still not done with them. So I think that we need to decide what are the boundaries that I'm still working with the data set. Recently, we published that paper in Science where we more or less suggested that for genomics and other related fields, publicly available data should become far more unrestricted, and they should be aligned also with the reward system. There's a tension between data producers and data users or data analysts, and sometimes I have heard quotes like from Jeff Drazen. He once said that these data analysts are research parasites, which obviously he recanted his position. It was not very nice. Now, I think a better way to see data analysts is movie directors, and probably you can see data generators as screenplay writers. Sometimes the screenplay writer and the movie director is the same person, but it doesn't have to be the same. And very often, it may be that data generators can only produce very thin slices of data that no matter what they do in terms of analysis, they cannot really get very far. The viewpoint that they would get from that thin slice is very limited. Conversely, if you have hundreds and thousands of data generators who can contribute, for example, sequencing information to a much larger data set, the composite analysis starts having some meaning. It makes sense. It can tell us something that none of the little bits and pieces, the little slices, would have been able to tell us. So we need to arrive at a model of collaboration where you may have people who are screenplay writers, others who are directors of the movie, others who are taking care of photography, others who are taking care of being the actors, others of being the support staff, and all of them will be in the headings of the movie at the end of the day. There are some opposing trends at the same time. I think that we do see a lot of movement towards more reproducibility and more openness, but we do see also some other approaches that suggest that, well, now we have so much data that we don't need to worry about the scientific method. Somehow the data will give us the answer. We don't need to share. We just need to move fast and analyze them, and they will just be okay. And the Theranos story that Uli mentioned was pretty much along these lines. The company never published anything about what they were doing. They were just telling that we're saving the world and we're doing that at fast pace, and you don't need to know about how we're saving the world, but we are saving the world. And obviously that was not the case. Actually, Theranos is not an exception. People say that it is an exception because it was clear fraud. Well, this has not been decided in court yet, but even if it is, recently we looked across every single unicorn that is operating in the health research space, and we found that many of them have a very similar profile of lack of publication and sharing of evidence as Theranos did. I'm not saying that it is fraud, but we just have a gap of data, of information, of evidence on which we can base and have some trust for the valuations that exceed $1 billion in each one of these cases. In the balance, we do see progress. When we took a random sample of the entire biomedical literature from 2000 to 2014, we saw that data sharing was very, very rare, and other reproducibility practices were also pretty uncommon. When we repeated that exercise for the period 2015 and 17, we saw some clear improvement, in particular for data sharing. And I think the improvement is real because many journals explicitly started having these policies in place. Many professional societies pushed in that direction. Many funding agencies said that we want to make that the norm. This is one example from psychology where psychological science with the thick line very rapidly increased the uptake and the proportion of papers that were reporting and making available raw data. And this goes to 2015, and it went up from 4% to 40%, and now in the latest quarters it's up to about 75%. Across the entire biomedical literature, you also see substantial movement from close to 0% in 2000 to almost 25% by 2017, and clearly an upward slope. Some other components of transparency are also improving. For example, disclosure of funding and disclosure of conflicts of interest was happening in the minority about the beginning of the century, and now it happens at about 70% of the papers that are being published. Claims of novelty are always very common. So if you just look at the opening of the paper, they very often still say that we have something novel to say. But we do see papers that claim that they're including replication in their effort, and I think that this is also a good sign. Efforts to enhance the reproducibility of computational methods are underway, and we see more journals that are asking for sharing not only of data but sharing of code and software, and taking some steps to make sure that indeed that sharing is happening. The easiest thing would be to just click on that link that says the software can be accessed here or the code can be accessed here. Make sure that you don't get an error sign. But if you want to spend more time, obviously you can go through a full reanalysis evaluation. There is tension between transparency and complexity, and some of the tools that are becoming more popular, I think, are becoming less transparent. So there's a whole literature, for example, in artificial intelligence that is growing very fast in terms of applications. To be honest, I haven't seen clear major improvements in performance in most of the cases where artificial intelligence methods like deep neural network algorithms are compared against a plain vanilla logistic regression. The increment in performance is pretty slight, but it creates a new generation of tools where they are based on complexity, trying to model very complex interactions and interplay between multiple factors, but they're not so easy to be transparent. So we need some extra effort to see how we can maximize transparency about these more complex models. We need to educate people on different methods, and this means that besides transparent and hopefully registered whenever possible statistical analysis plans, we need to work through the rampant illiteracy and innumeracy of many, many papers. I mean, you see that methods are misused and misinterpreted. We need to see how we can promote the use of some standard features in research. For example, for in vivo animal studies, there is some improvement over time in the use of blinded assessment of outcome and randomization, but we still have substantial way to go to really reach a point where the vast majority of studies would have blinded assessment of outcome and a randomized design. There's an ongoing statistics war, as you may have heard or read or Googled or tweeted or seen in other social media, and there's probably lack of agreement on what is the exact transformation of statistical methods that we need to apply. We all agree that statistical methods are misapplied and misinterpreted, and I think that p-values are tremendously misinterpreted and people misunderstand what statistical significance is. There's a great variety of alternatives, and I think that it is nice to see these alternative ideas and see how we can fit the best methods for the best purpose each time. Containing the influence of conflicted stakeholders and authors is another step that we can take. As I mentioned, we do see improvement in the disclosure of conflicts of interest, but there's also some bigger questions, like who should be the sponsors and authors of some sensitive types of studies, like randomized trials, meta-analysis, cost-effectiveness analysis, or guidelines? Should we allow sponsors who would benefit or professional societies whose existence depends on what these guidelines or what these studies say to be the ones who lead the way in drafting these important documents? Finally, my bias. We need research on research. We need meta-research to evaluate how to make things better. Just because one idea sounds to be very nice, it doesn't mean that it will work. So we need research on how to perform, how to communicate, how to verify, how to evaluate, and how to reward research. And this is pretty much what Metrics and Metric B are doing, and what many other teams around the world are interested to do. I will close with some thoughts about the reward system, because this is really probably a key driver in implementing and sustaining the changes that are being proposed to improve research methods. Sometimes we may study reward practices and incentives with randomized trials, but occasionally it may be very difficult because they may be very complex, and it's even difficult to define the population. But we can have some additional insights from modeling, for example. And this is one such model that I created with David Grimes, where we have 11 equations that describe a universe of science. And that universe of science basically includes three types of researchers. We have a diligent cohort, which is the majority of scientists. We have some who are careless, and different surveys disagree on how common that is. Surveys that ask how often are you careless give pretty low rates, but surveys that ask how many have you seen careless scientists in your vicinity, in your environment, give very, very high rates. And finally, very rarely you have unethical behavior like fraud, and I would say this is probably less than 1%. So we run that model with rewards for people based on what they can produce. And if you do not reward the diligent cohort or do not penalize those who are unethical or careless, the careless and the unethical cohort has an advantage. They have a competitive advantage. They can get there cutting corners. They can get there faster. So if they generate progeny with the same standards of how research should be done, within a few generations of funding cycles, you will get the diligent cohort to start declining and the unethical and careless cohort starting becoming dominant. You don't need to have 11 weird equations to prove that. I think that it's very obvious that we need to reward the best science. And what is the best science, I think, is the big question. Until now, most of our reward systems are focusing on productivity, rewarding people who publish more, and I'm perfectly fine with productivity. I like to publish. If you tell me don't publish any longer, I will go through major depression, and antidepressants may not work very well, so please don't do that. But besides productivity, we need to focus on quality, on reproducibility, on sharing, and on translational impact. And this creates a PQRST electrocardiogram of improving the heartbeat of scientific research at large. Do we need evolution or revolution? Probably we need both. We need to find opportunities to improve defects and opportunities to grow the way that we apply research practices within fields and across fields. And we need to get buy-in also from multiple stakeholders. It's not just scientists who are working on science. There's lots of funders, there's lots of private investors or industry, there's journals, editors, publishers, societies, universities, non-for-profit institutions, non-scientific staff that have an interface with research, hospitals, insurance companies, governments, state, federal authorities, and people who care about science in very different ways. And we need to find ways to align the interests of all these stakeholders towards better research that can really be more reproducible and useful. To conclude, discovery and replication are part of an integral continuum. I think it's false to try to separate them and create two classes of research, two classes of scientists. It has to be united, and that continuum is hopefully working towards reliable and hopefully useful scientific knowledge. The reproducibility and the usefulness of many disciplines of scientific investigation has substantial room for improvement. And we do see some movement at the moment. Over the last several years, many of these indicators seem to have improved. There are many possible interventions that may improve the efficiency of research practices and the reproducibility and utility of the evidence. And I still believe that transparency, openness, and sharing are likely to help, but details on how to exactly do that can be important. So we do need more research on research. Many thanks to a number of my colleagues who have contributed to some of the empirical work that I showed you today. And also many thanks to all of you for being here today and for listening. Thank you. Vielen Dank.